Example here. All right, the AP really likes to test, do you know, not just can you just like do mindless calculations, all right, but do you actually know the theorems and all the stuff that we're talking about? So this is an example of one of those. The table above gives the values of a function f at selected values of x. Which of the following statements, if true, would be sufficient to conclude that there exists a number c in the interval 2 to 11 such that f of c is equal to 8? All right, so what you're really looking for is if you see one of these things where, hey, which one of these would be sufficient to conclude, kind of thinking about, hey, something that proves something, it's probably going to be one of the theorems. Okay, and we've talked about what? Intermediate value theorem and squeeze theorem, I believe. All right, there's a few more theorems we'll talk about. All right, so would it be sufficient to conclude that there exists a number c in the interval such that f of c is equal to 8? All right, so that mirrors definitely, hopefully, we can think about it, that mirrors the intermediate value theorem. All right, that there's some number on an interval such that f of c is equal to a number. All right, so we got to think about all the things the intermediate value theorem you had to have in order for the intermediate value theorem, I can't even say it, intermediate value theorem to be true. All right, and so one of the things is I had to have an f of a and f of b value. The y values had to be one was less and one was greater than 8. Is that true here? Yep. Okay. I go 5 down to 2, up to 6, up to 12, and down to 10. All right, so intermediate value theorem, okay, if we can apply it here, means that somewhere between 6 and 8 there would have to be an 8. And somewhere between 9 and 11 there would have to be an 8. There could be some other places, but we know they have to happen there because I'm going from 6 all the way to the 12, so I've got to pass 8 to get there. All right, actually I only have to have it in this one place. So all those of you are shaking your head in agreement. You're just trying to say, yeah, that's what he wants to do, is have him shake my head in agreement. All right, so it has to happen there between 6 and 9. Okay, because the y values go from 6 to 12. All right, if we can use the intermediate value theorem. So let's look at our answer choices. F is defined for all x's. F is increasing, or f is continuous. All right, so let's look at number 2 first. F is increasing. All right, what does that mean for a function to be increasing? It's always doing what? Going up. All right, does it have to be increasing for that to work? Or can I have an increasing function from 6 to 9 where it's always increasing, but it does not get 8? All right, it turns out we can. It's a little weird. All right, but if I were at, say, here's 6, here's 9, all right, and I'm here at the value of a y value of 6, and at 9 I'm up at 12. All right, I could have a function that, hey, I'm going here, I'm increasing. All right, and I'm still increasing, yes. All right, but I could have totally skipped over 8. It's increasing the whole time, okay, but it totally skipped over it. Okay, so even though that does kind of seem like, hey, that would need to be true, it doesn't necessarily have to be true. Okay, or if it's true, it doesn't necessarily mean that that's going to work. All right, and kind of the same thing for number 1. All right, the function is defined for all variables or for all x's between 2 and 11. All right, this graph I drew over here also makes that true. Okay, I'm defined for all the values in between here and here. All right, but then I have a little jump discontinuity but the x is still defined, the function is still defined at that x value. All right, but the one our correct answer is our second number 2 here. Left an I off. All right, the f needs to be continuous. All right, and so if you really know your theorem really well, from a couple of slides ago, all right, I even underlined it there, f has to be continuous for the intermediate value theorem to apply. Okay, so knowing that theorem like the back of your hand, okay, is really, really helpful. All right, so if something is continuous, then I have to pass through 8. If it's not continuous, then it's not necessarily true. So that would be a sufficient condition. All right, to finish out the lesson, we're going to talk about a corollary to the intermediate value theorem. All right, and all it does is it just puts f of a and f of b in certain places. Okay, it says if f of a and f of b have opposite signs, okay, so one's positive and one's negative, or in other words, if you multiply them together, you get a negative number. All right, then there's at least one number in between the a and b such that f of c is equal to 0. Okay? It's the intermediate value theorem. We're just saying, hey, instead of looking in between any two y values, we're looking in between a positive value and a negative value. All right, and so all it says here is if I have one negative y value and one positive y value, that curve has to cross the x-axis somewhere in between there. All right, it turns out to be a pretty important result, okay, because that's how we can find places where a curve hits the x-axis when it's not easy factoring to do. All right, so let's look at this example here. We're not really going to have to actually find them. All right, but it says selected values of a continuous function are given in the table above. What is the fewest possible numbers of zeros in the interval from -4 to 4? All right, and so what I'm looking for is where do the y values go from negative to positive and from positive to negative. All right, so that occurs right here between x values of -4 and -2. The y values go from negative to positive. Also happens in between 0 and 2 because the y values go from 6 to -1. It also happens between 2 and 4 because the y values go from a negative to a positive. All right, so the intermediate value theorem says there has to be at least 3 zeros. Okay, zeros being a synonym here for x-intercept. There could be more, but I know there's at least 3. All right, would it be okay if I asked that kind of question on the test?
Is that the answer?
That's the answer.
Yes.
Okay? All right, let's look at this one. Show that there is a root, another synonym for x-intercept or 0, of the equation 4x to the third minus 6x squared plus 3x minus 2 equals 0 between 1 and 2. Doesn't tell me to find it, okay, but says show that there's a root. Okay, so first thing off, I need to say, hey, if we were to call a function 4x to the third minus 6x squared plus 3x minus 2. All right, so if you set f of x equal to that, all right, we can say that f of x is continuous. All right, we need that continuity part of the function in order for intermediate value theorem to work. And f of x is continuous because it's a polynomial. All right, and the next thing we need to do is we need to find what f of 1 is. All right, what happens when we plug the 1 in? This is our interval we're looking at between 1 and 2. F of 1 would be 4 minus 6 plus 3 minus 2. Which would be negative 1. Good with that? All right, and then plugging 2 in, I get 2 to the third, which is 8, times 4, which is 32. Minus 2 squared is 4 times 6, which is 24. 3 times 2 is 6. Minus 2. Which is what? 12? All right, and so we can say since f of 1, which is equal to negative 1, is less than 0, which is less than 12, which is our f of 2, the intermediate value theorem, the IVT, guarantees a 0 of the function occurs on the interval one to 2.
So basically we're trying to find if 0 to 0 between, if the exponent, the equation will go through 0 between 1 and 2.
Yeah. Yeah.
Is it because it says between 1 and 2 that it's not negative 1 is less than or equal to 0? You think it can't be right on 1?
Yeah, I mean, I could actually throw some parentheses on the 1 and 2 there, because I know it's going to happen at 1 and 2.
Well, because it says between, you can't.
Yeah. I mean, I'm not saying anything false. I could be a little bit more specific, but yeah. All right. Now, this is actually what your calculator does. Okay, anybody ever found the answer to a where a graph crosses the x-axis using your calculator? All right. That's actually what your calculator does. Pull up my calculator over here. There's half of it. There's the other half. All right, and so if I wanted to find the zeros of x to the fifth plus 4x squared minus 9x plus 3. Okay, what the calculator actually does is uses a method called Brent's method. All right, I've never done Brent's method. I just looked it up. Okay, but what Brent's method does is it uses method of bisection and some other advanced techniques in order to find the zeros. Okay, and so what it does is it says, all right, let me find one point that's positive and one point that's negative. All right, and therefore, by intermediate value theorem, I know something has to happen between those two, right? All right, and then let's bisect that interval and find that y value. Okay, if it's positive, then that replaces our positive value. And we look again, we bisect it again. And we continue bisecting until we get the right answer. Yes?
On some of the other ones, how did you know there was a zero? Couldn't it have jumped over the x-axis?
Oh yeah, I was about to ask that. Isn't the last one didn't say it was like continuous? So I was wondering that also.
On this one right here?
Yeah, it didn't explicitly say it was continuous.
All right, but because it's a polynomial, we had a theorem earlier.
Like whenever you go to the tables, why can't the tables have jumps?
It'll explicitly say it's continuous.
So the only one where it didn't say it was continuous was just for the polynomial.
Oh, okay.
This one right here didn't say it's continuous, but since it was a polynomial, it was continuous.
Okay, so every time it's a polynomial, it's always going to be continuous.
Yes. All right, I think if you look back at your notes, several pages back, there we go. Right here, this one says that all of these different functions are continuous in their domain. Polynomials, rational functions, roots. Okay, so most functions are continuous. Okay, the only ones that aren't continuous are our piecewise functions. Okay, and that greatest integer function. But most of the ones you're going to deal with are continuous. All right, so again, what the method of bisection does, it says, hey, on this problem right here, and we're not actually going to do it out. Okay. It says, hey, I know that at f of 0, or at 0, I'm positive. And at 1, I'm what? Negative. All right, the method of bisection is, all right, let's see what happens at 1/2. All right, 1/2, that y value is what? Looks like it's negative.
I see you just keep splitting and trying to get closer
Mm-hmm.
and closer until you get it.
And so now we're going to look in between here and here. Let's split it again. All right, so that value is now positive, so now I'm going to look what? Between these two. All right, and it just keeps on doing it until I get sufficiently close to 0. Okay, and the calculator has a threshold of the number of zeros, or number of decimal places. It needs to be 0 in order for it to be considered the actual 0. Okay, we could spend some time doing that, but in order to find those values, you'd have to use a calculator anyway. All right, but this is what your calculator does. Okay, and you've done it. All right, if you were to go and use your calculator, if I can get to my screen. All right, and we were to type that equation in there. All right, so type that into y1. As I'm pressing lots of buttons I don't mean to be pressing. There we go. I type that in there, x to the 5th plus 4x squared minus 9x plus 3. I graph it. There's my graph. Okay, let me zoom in a little bit. I'll zoom box it. I'm just going to look at this one right here. Calculators are a little buggy. All right, but if I wanted to find this 0 right here, all right, you can trace it and just kind of get close to it. All right, but if it's not a nice, lovely one, you can't really exactly find it. But if you hit second trace, all right, that number 2 finds the 0 for you. All right, so second trace 2. We all familiar with that? Awesome. All right, and then what do you have to do? It asks you questions, doesn't it? It asks you what? Left bound and right bound? All right, and so it is left bound and right bound, but what is it doing? You're trying to find values where one of the y values is positive and one of the y values is negative. Okay? It's using that intermediate value theorem. If I can get my calculator to, there we go. And I want one of them positive and one of them negative. And then when you guess, it really doesn't matter. Technically, if you guess closer to the right answer, it does it quicker. All right, but it's a calculator, it does it pretty quick anyway. All right, and it tells you what the 0 is. Okay, but it's using that intermediate value theorem. If you don't find one that has a positive and one has a negative, then it's going to say error, there's no such 0 in there. Okay, the calculator is using intermediate value theorem. All right, so that is, I believe, the end of those notes. All right, questions on that?
What are we going to have to round to if we use this calculator?
3 decimal places. 3 decimal places. Okay, and I'm not going to ask you to find zeros right now. We'll do plenty of that later on.